VibeRo is a Vibrotactile tool connected with a head-mounted display to provide the haptic feedback that can generate illusions of squeezing objects with various stiffness coefficients. Before going further, let's shed light on the theory behind the haptic illusions. Vibrations are undoubtedly important to us as we discriminate different surface textures, detect a slip of a grasped object, and even infer a limb displacement, all due to being able to sense the vibrations that occur at the contact points. There are four primary tactile mechanoreceptors: Merkel's discs, Ruffini endings, Meissner's corpuscles, and Pachinian corpuscles. The last detect transient pressure and high-frequency vibration. Detected vibrotactile stimuli go through the nerve and cause haptic illusions. This trick is widely implemented on the latest smartphones, video game controllers, car interior interfaces, and wearable electronics. In other words, everywhere where we need to give a sense of touch, as actions as tapping, pressing, rotating, and sliding over various textures. So in our case, haptic illusions is reached with VibeRo and Oculus Rift goggles. The enclosing structure of our device was 3D printed from liquid polymer resin. The haptic system consists of two main parts: a force-sensitive resistor and a voice coil actuator. The FSRs measure the applied normal force. This force modulates the oscillating frequency of the voice coil actuator. Two springs isolate vibrations and ensure that the most amount of vibrations propagate to the user's fingertips through the side parts. With VibeRo, we can imitate actions like a squeeze of a soft granular object, for example a rubber sack filled with a granular particles such as coffee grains. In addition to the device itself, we created an environment in VR using the Unity game engine. Through HMD, a user can see a virtual hand model and a virtual soft object. The object consists of a set of tiny particles connected to each other as in real-world physics. The deformation of the soft object is modeled in real time with the use of force values obtained by FSR. A combination of the hardware and VR parameters give us 18 working modes that differ by vibration frequency level, a range of applied force, and VR animation speed. Experiments with 10 tests show that amplification is usually larger at lower oscillation frequencies. Also, a larger limb displacement is sensed for a higher force threshold values. To sum up, it has been revealed that varying the ratio between the rate of change of the motor frequency and the rate of change of the shape of the soft object seen in a HMD renders stiffness parameters of the soft object to the rigid handheld controller.